Okay, so now the next thing that we have here is basically this part, this exercise, which says that we want to check the following statement, whether the statement is true or false, by proving the contrapositive. And basically the statement is, if x and y belong to the set of integers such that xy is odd, then both x and y are odd. We want to see whether that's true or false. So if I take P as xy is odd, this statement here, and Q as both x and y are odd, this the second statement over here, then we have to check whether the statement P then Q, we have to check whether the statement P then Q is true or not by checking the contrapositive. By checking the contrapositive, which is not Q, then not P. So we want to see whether this statement is true or not, meaning that if xy is odd, then both x and y are odd. We want to check the validity of this statement. Now, to check the validity of this statement, we need to check the contrapositive of this statement. As we said, this was the second method that we talked about. Let me write this properly. Not Q then implies not P, which is basically called the contrapositive. Now, for the contrapositive, we need to assume that we need to make an assumption. And the assumption that we want to make is not Q, the negation of Q. So, basically not Q is this statement. So you can, if you want to basically negate this statement, you can say that it is false. It is false that both x and y are odd. And this implies that x or y is even, meaning that either x or y is even. So then x is equal to 2n for some integer n. Then you can write x as 2n for some n belonging to the set of integers. And therefore x times y is equal to 2n times y. 2n times y for some integer n. For some n belonging to the set of integers. Now, if x times y is basically 2ny for some integer n, then of course it's an even number. X times y is an even number, which is basically the opposite of, the negation of P over here. Here we said that xy is odd, but here we can see that xy is actually even, because you can write it as 2 times x times y. And since it's a multiple of 2, it's an even number. So then that basically means that not P is true. That basically means that not P. This shows that, therefore, you can say that not P. So P is xy is odd, but here I can see that xy is even. So not P is true. Not P is true. And thus we have shown that not Q. Thus we have shown that not Q implies not P. Not Q implies not P, and hence the given statement is true. And hence the given statement is true. is true. Now what happens? Now what happens if we combine, when we combine an implication and its converse? Let's see what happens. I really don't know what that's. Let's see if we happen. Basically, what happens when we combine an implication and its converse? Let's see what that is. So let's consider the following statements. So for example, you have P is a tumbler is half empty. A tumbler is half empty, and Q is a tumbler is half full. So P is a tumbler is half empty and Q is a tumbler is half full. And we know that if the first statement happens, if P happens, then the second statement happens, and also if the second statement happens, then the first statement happens. I don't understand this. Okay, so now basically in this situation, so what happens is that you have two statements. The tumbler is half empty and the tumbler is half full. So now suppose that in this situation, if P happens, Q happens, meaning that if P, then Q, and if Q, then P. So if you have both of these, basically, if P happens, then Q happens, and if Q happens, then P happens, we technically say P if and only if Q. Or you can also, basically logically, you can also say Q if and only if P, that you can also say. Now this is denoted by P if and only if Q, and this is Q if and only if P. So this is called a biconditional. But I don't really know why they have basically mentioned this here, because basically this kind of thing you usually learn in, for example, you usually use it in geometry. Okay, so we said that I said that I don't really know why they have basically what they have mentioned in this example here. Because you usually use this in geometry. For example, you say that if you have for example, if you have some triangle, suppose that you have an isosceles triangle. In an isosceles triangle, these two angles are equal, are always equal. So then you can say that in an isosceles triangle, the two base angles are equal. And also, if you have a triangle in which the two base angles are equal, then it's going to be an isosceles triangle. So you can say it both ways. So when that happens, then you can say that if you basically, for example, take P as, for example, if you have an isosceles triangle, basically in an isosceles triangle and Q, the two base angles are equal. So now P and Q, so we said that basically if P then Q is true, because if you say that if P then Q, what that means is that if in an isosceles triangle the two base angles are equal. And also we said that Q then P is also true, meaning that if you have a triangle in which the two base angles are equal, then it's going to be an isosceles triangle. Then technically you can put these together and write, for example, P if and only if Q. And so this is you can call this only if, and this is if and only if and only if, right? So that means that if P is true, then Q is going to be true. If Q is true, then P is going to be true. If Q is not true, P is not going to be true, and if P is not true, then Q is not going to be true. But you don't need to bother about this right now, I suppose, because this discussion goes to nowhere. Now there is another method that you can use in order to basically validate your statements, which is called biconditional. Now let's see what contradiction is. And basically contradiction is also some way that we use in mathematics for many kinds of purposes, for proving things, for disproving things, and so on and so forth. And I suppose mathematics has been developed based on the fact that, well, of course, this is not a statement that is, I mean, mathematics is of course much more complex than it can be explained by one simple statement or anything like that. But of course you can say that as a valid statement, I can say that in mathematics contradiction is not supposed to exist. If there is a contradiction, that means that there is something wrong. Contradiction is not supposed to exist in mathematics. So we use that fact, the fact that contradiction is not supposed to exist, and then using that we assume something, and then using that assumption, then we will see that there is a contradiction, or as a result of that assumption we say that basically we see that there is a contradiction. And so based on that, we conclude that assumption was not right, because the contradiction was the result of assuming something wrong. And so now you have assumed something, that assumption is wrong. That means that the negation of that assumption is actually true, right? So that's basically how this works. So now by contradiction, here to check whether a statement P is true, we assume that P is not true. So for example, you have some statement P. You have some statement P and you want to check whether this statement is true or not. So you assume that P is not true, meaning that is basically not P is true. Okay, so that means that not P is true. And then we arrive at some result which contradicts our assumption. So here we assume that basically this was what our assumption, which is basically not P is true. This was our assumption. So then, after going through some algebra or geometry or something, some for example construction work or something like that, construction meaning drawing figures, geometric figures and things like that, you arrive at some result that contradicts your assumption. Some result contradicting your assumption. Now, if your assumption is contradicted, that means that your assumption was wrong. That means that now if not P, so based on this I can assume that not P is false. And that means that basically P is true. And that's what I wanted to show over here. I wanted to show that P is true. So that's basically the whole process. So for example, so now as an example, I came through one example, but I got kind of interrupted. So as an example, you want to verify by the method of contradiction. Verify by the method of contradiction. By the method of contradiction, that basically what you want to verify is a statement P, which is square root of 7 is irrational. Is irrational. So when you want to verify that square root of 7 is irrational, so by the method of contradiction, we said that we need to assume that basically the square root of 7 is rational, meaning the negation of this statement, meaning that we assume that not P is true. That is, not P is true, meaning that basically P is square root of 7 is irrational. So then if not P is true, that means that the square root of 7 is rational. Now if a square root of 7 is a rational number, what that means is that basically what that means is that there exist basically positive integers a and b, okay, so basically we said that the square root of 7 is so basically the assumption that we made was that the square root of 7 is a rational number. Now if the square root of 7 is a rational number, what that means is that there exist basically positive integers a and b such that the square root of 7 is equal to a divided by b, because basically based on the definition of rational numbers, a rational number is basically a number that can be expressed as the ratio of two integers, and these are by definition are two integers. So but we can basically define a condition here, and write where basically where A and B have no common factors, have no common factors. Now, if I have the square root of 7 is equal to A divided by B, I can square both sides of this equation, meaning that I can write basically the square root of 7 whole squared is equal to A divided by B whole squared. And that gives me basically 7 is equal to A squared divided by B squared. So A squared is divided by B squared. Now, and that in turn means that A squared is equal to 7 times B squared. A squared is equal to 7 times B squared. So what that means is that A is a multiple of 7, or you can say basically A is a multiple of 7. A is a multiple of 7, or you can say 7 divides A. 7 divides A. So if 7 divides A, then therefore basically you can, based on this, you can say there exists an integer C, since A is an integer. So then you can say that if 7 divides A, or A is a multiple of 7, when you say A is a multiple of 7, meaning that means that A is equal to 7 times something. Now that something could be 1, could be 2, could be 3, could be 4, could be -1, could be -2, but it has to be some integer, because ultimately you want to get some integer over here, and the product of two integers is an integer. So what that means is that I can write if A is a multiple of 7, then I can write basically A is equal to, so then I can say therefore there exists an integer C, such that A is equal to 7 times C, because A is a multiple of 7, and A is equal to 7 times C. So if I square this equation, I will get A squared is equal to 49 times C squared, and over here we already know that A squared is equal to 7 times B squared, which means that 7 divides A. I'm sorry, no. So using these two, what you can conclude is that 49 times C squared is equal to 7 times B squared, because both of them are equal to A squared. Then you can simplify, can divide by 7, you will get B squared is equal to 7 times C squared. B squared is equal to 7 times C squared. Now if B squared is equal to 7 times C squared, that means that 7 divides B as well. 7 divides B. Now we have already shown that 7 divides A and also 7 divides B, meaning that A is a multiple of 7 and also B is also a multiple of 7. So this implies that 7 is a common factor of both A and B. that implies that 7 is a common factor of both A and B. And which contradicts our assumption that A and B have no common factors. This is important, which contradicts our earlier assumption that you can see that this is a very clever way of proving this. Our earlier assumption that A and B have no common factors. Now this shows that, so this basically shows that the assumption square root of 7 is rational. That's basically the assumption that I made over here. I said that square root of 7 is a rational number. That was the assumption that we made. So that was the assumption that I made. So the square root of 7 is rational. That makes this assumption wrong. So that shows that the assumption the square root of 7 is rational is wrong. Hence the statement the square root of 7, hence the statement square root of 7 is irrational. Is true. So the statement that square root of 7 is irrational, I put them in double quotes, hence the statement square root of 7 is irrational is true. So that is basically, for example, how you prove something by the method of contradiction. Now the method of contradiction works in geometry. For example, you want to show that a point, for example, you have some triangle over here, and for example you want to show that for example there is some line going through these two sides. You want to, for example, let's call this point P. Now you want to show that, for example, this line, let's say AP, cuts, for example S, R, for example, Q. You want to show that AP cuts this line RQ exactly at point P, exactly at this point. Then, for example, in such cases, what you can do is that you can assume that basically, well, based on the construction, that all of your conditions have to come together, of course. But then, based on your assumption, then you kind of assume that for example, this line is going through RQ, for example, at some point P prime. And then, using the method of contradiction, you can you can basically, and then of course, since P and P prime are two different points, then you will assume that basically, then of course, then you make the assumption that P and P prime are two different points. And then once you do some geometry and you do some proving and so on and so forth, you will see that, for example, the point P and P prime are actually the exact same points, meaning that point P, basically you will find that P is equal to P prime in that construction. And that basically contradicts your assumption that P and P prime were different points. And that is basically how, for example, you use the method of contradiction in geometry. I've seen it a couple of times in geometry. And, well, many other places, of course. It's all over mathematics. So now the next thing that we shall discuss is a method by which we may show that a statement is false. Next we shall discuss a method by which we may show that a statement is false. So now we want to discuss a method, a method by which we may show that a statement is false. Okay. Now the method involves giving an example of a situation where the statement is not valid, which is actually interesting. So this method involves giving an example of a situation where the statement is not valid. Such an example is called a counterexample. That's also used in mathematics. So that's called a counterexample. Counterexample. So what that means is that, for example, using a counterexample, for example, you want to show that, for example, you have a statement, for example, P, all prime numbers are odd, for example. Now you know that prime numbers are basically 2, 3, 4, not 4, but 5, 7, 9, there is no 9, there is no 10, there is 11, there is 13, and so on and so forth. Now if you write out these numbers, what you will find out is that all of these prime numbers are odd. All are basically odd, except for this number 2. 2 is actually a prime number, and 1 is neither a prime number nor a composite number. It's a funny number, really, when it comes to prime and prime and composite. So, but 2 is actually a prime number, because you can write 2 as 2 times 1, right? So 2 is a prime number, and 2 is a prime number and also an even number. Except for 2, all of these numbers are basically all of these numbers are odd numbers. The only prime number that you can find is 2. So now the statement that I have is that all prime numbers are odd, and you want to basically using a counter example, which would be, for example, in this case just a 2, you can show that you can give an example of a situation where the statement is not valid, which would be possible by providing the example 2, and that basically makes that statement false. Meaning that, as you can see, for example, over here, all the prime numbers that you could ever find are all basically odd numbers, except for only two. And so even if there is even one counter example that you can supply in the case of that situation, that makes your statement false. And that's basically how you use a counter example. Now, the name itself suggests that this is an example to counter the given basically statement. So some example to counter the given statement. As an example, let's say by giving a counter example, show that the following statement is false. If n is an odd integer, odd integer, then n is prime. So if n is an odd integer, so you have basically all of these integers, positive, negative. That's exactly what I said over here, but I changed it a little bit. I said that all prime numbers are odd. Here we said the statement is if n is an odd integer, then n is prime. Okay. So now the solution is the given statement is in the form if p then q. So you have if p then q. We have to show that this is false. For this purpose, we need to show that if p then not q, so you need to show basically to prove this wrong or to prove this not true, you have to show either basically if p, you have to show or prove that if p then not q, or you can also show that if not q then p. That you can also show, I suppose. But let's go with this way of proving. So you can show, so you need to show that if p then not q, and that makes this statement false, right? Now to show this, we look for an odd integer n which is not a prime number. For an odd integer n which is not a prime number. Of course, this example is a little bit different, of course, completely different from what I said over here. Let's forget about this for now. So in order to basically to show this, we look for an odd integer which is not prime, which is not a prime number. So then, for example, you could for example go for 9, for example. You could go for 9. 9, if n is equal to 9, then basically we said that if p, then 9 is supposed to be a prime number, which is not a prime number. And that basically proves your statement wrong, or basically false. So n is equal to 9 is a counter example. Thus we conclude that the given statement is false, that this statement is actually false. So in the above, we have discussed some techniques for checking whether a statement is true or not. And there is a note over here that says in mathematics, counter examples are used to disprove the statement However, generating examples in favor of his statement do not provide validity of the statement. Meaning that you basically, if you want to prove something, you don't, for example, start generating basically examples that prove the case to be true, because I mean, in most cases, in almost every case, you can generate innumerable number of examples that prove that the case is true. But then, even if you find one counter example, that counter example disproves your statement completely. Even if you have found, for example, 1 million examples that do prove that your statement is true. So you need to be careful about that. Now, in the next video, we will talk about exercise 14.5, and then we have some other examples as well that we will go through as well. So I'll see you in the next video.